Welcome to Study Loop.
Hello friends, here it is given an ideal gas refrigeration cycle. With air as working fluid. Assuming steady operating conditions exist, and second, air is an ideal gas with variable specific heat. No change in kinetic energy and potential energy. Find rate of refrigeration. Net power input and coefficient of performance. Let us hear the analysis. From the air table, A17E at temperature 500 R, enthalpy is 119.48 BTU per pound mass, and pressure of air is 1.0590 at temperature T3, 580 R. Enthalpy is 138.66 BTU per pound mass, and pressure of air 1.7800. So we can write PR2 to be P2 upon P1 into PR1, that is 30 upon 10 into 1.059. So it is to be 3.177. Hence, at pressure PR2 to be 3.177, Temperature T2 is 683.9 Reaumur and enthalpy to be 163.68 BTU per pound mass. PR4 to be P4 upon P3 into PR3. P4 is 10, P3 is 30, 1.78, so it is to be 0.5933. So at PR4 0.5933, temperature is 423.4 Reaumur and enthalpy to be 101.14 BTU per pound mass. So rate of refrigeration is defined as mass flow rate into heat transfer at low temperature, that is mass flow rate into H1 minus H4. Putting the value, mass flow rate is given in the problem, 0.5 pound mass per second into H1 119.48 minus 101.14 BTU per pound mass. So you will get 9.17 BTU per second. This is the refrigeration rate. The power input total will be power input of compression minus power input, power out of turbine. So net power input will be mass flow rate to H2 minus H1 plus, it would be a minus mass flow rate into H3 minus H4. Putting the value, all the values are given, just we have to substitute the 0.5 into 163.68 minus 119.48 minus 0.5 into 138.66 minus 101.14. So it is to be 18.79 BTU per second. Sorry, I have written wrong calculation. It is to be 4.73. 3.34 BTU per second. Coefficient of performance is defined as flow rate of heat upon net power input. 9.17 upon 3.34, so it is to be 2.75. That's all.